So Monday we looked at determining a rate law using some initial concentrations and initial reaction rates. And we looked and we had one that was zeroth order. What does that mean? How could we tell it was zeroth order?
Does it have an effect on the rate?
Right, we changed the concentration, it had no effect. And then the other one we doubled it or we tripled it, and it went up by a factor of 9. We figured out that it was second order, right? And I said you can probably figure out the rate law by looking at it. What I meant to say was by inspection, where you just kind of look at the numbers and you can kind of do it in your mind. So this one here I chose because it's a little messy. What does that mean? A little messy. So the first thing we want to ask is, what is the rate law? Well, we can write one, which is variables. Rate is equal to some constant, concentration of A raised to some power, concentration of B raised to some power. Once we know what those reaction orders are, we've solved the rate law. So I said the easiest way to do this is to come up with something that has what I call a rate factor is equal to a concentration factor raised to some power. So let's determine what's going on with reactant A first. And if I say, what effect does the concentration of A have on rate? What I want to do is choose where I'm holding a B constant. Then that will be having no effect on rate. So that looks like
Run 1 and 3, right?
right 1 and 3. We need to use our calculator. Looks like I've done something to the concentration here. What effect did that have on rate?
Nothing. No.
So why don't I just use these first two experiments? And so my rate factor, I want to put the larger rate up top. Lower rate down below. Now my concentration factor, and the units typically go away in these ratios. So, all right, this doesn't look like something we can just look at, say what that is, until none of you got your calculators all warmed up. Nobody's telling me what it is. They're telling me I made a typo here. I don't want that to throw us off. Yeah, nobody's gonna look at that and say, well, that is a 1.7715 something. Now let's figure out what 0.402 divided by 0.302 is.
1.3311.
So what does x equal? Yeah, so there's two ways around this problem. One creative way is to say, well, I don't know. I know it's not 1 because anything raised to the first power is what? Itself. I know it's not to the 0th power because anything raised to the 0th power is 1. I got a squared button on my calculator. I'm going to poke that. When I square this number, I get that number. So I figured out that it's second order with reactant B. Alright, so when life is messy like this, we can't just look at this by inspection. We looked at it and figured out the 0th order of A by inspection. Now there is a mathematical way to do this, and that would be to take the log of both sides and use our property of logs. So there's a log identity that says I can do what with this x?
You can take it out.
I can put it in front, right? So now it looks like this. So now I can get my x right by itself like that. So in case we weren't inventive enough just to try some different values of x. So now if I go on my calculator, log, my calculator spits out this number. And we know it needs to be most likely a whole integer number, so yeah, we get a 2. And so this is important because in lab, when you do this, there's lots of experimental error. You might be able to see a doubling or a quadrupling, or you might not. All right, so now we've figured out the reaction order. We deduced the rate law. Now we know what it is. Rate times constant.
The reason you don't have to have the A in there is because it's at the 0th.
Right. Yeah, concentration of A has no effect on rate, so it doesn't show up in the rate law. The rate law tells us how concentration affects rate. Alright, more fun questions to answer. Solve for K. Or I could say, what is the rate constant? Now that we know the reaction order, we can choose an experiment. If the rate constant is a constant, it shouldn't matter which experiment we use. We're just going to plug in this rate, 0.5187, and now I might actually be more concerned with my units. There is the rate. It is equal to whatever we're trying to solve, concentration of B squared, right? So if I solve for X, I'm going to divide both sides by B squared, and it's going to go away from this other side. So now I want to match this up, this rate, this concentration, and I'm going to pull out my calculator. 0.5187 divided by 0.402 squared. Now the $1,000 question is, what units does this have?
Inverse seconds.
It has inverse seconds, and is that it?
Because the moles cancel.
Is the M moles or is that the big M?
That's molarity.
This one will cancel with this one, and we see those units like that. So in the electronic homework, or back of the book answer, it's a good time to look at my favorite slide here. We want units of rate. So depending on the reaction order, what that does to concentration. So our example problem we just did, here's our units of rate. Moles per second. We'll just say we're in a liter flask, so molarity and moles are the same. Molarity per second. And our concentration was in molarity, and it's squared. And here are the units of the rate constant. Reciprocal seconds, reciprocal molarity.
Did you say K is supposed to be the same for all three of them?
Yep. It shouldn't matter which experiment, and we could test it out. It might vary a little bit over here with some rounding, but you should be able to choose. All right, let's test it out. We do this for this one up here. How about 0.2928 moles per second divided by 0.302 squared? I was a little nervous here. Let's see what happens.
Pretty chill.
So the three digits, they're the same. And we still have the same units. Yeah, so the three digits, the number's the same. So now that we know we've solved for K, well, let's just say 3.21. Now we almost know everything there is to know about a rate law. The question might be, well, so what? And so this is all at the same given temperature. Now we might be able to ask another question. That's the exciting thing, is the questions we get to ask and then find answers for. So now we can solve for a rate at a concentration's not given, because now we know the rate law, and that's how concentration affects rate. So we'll say rate is equal to this rate constant, independent of A. We don't care what A is. We'll put this number in. So for me, the exciting thing is, what are our units going to be? How are our units going to be?
Well, since it's squared, would it be like M over S?
Right, and that's the unit of rate. Absolutely. So here goes, 0.5 squared. And as Nick said, we have a unit of rate.
So with that,
That cancels with like 2. You're left with the M and the S. Gives us units of rate. Yeah, so that's the beauty. We understand how concentration affects rate. Come up with any concentration that we desire. So at the beginning of this chapter, we looked at rate expressions. And I said you don't want to confuse a rate expression with a rate law. Well, now we use our expression of rate, the disappearance of reactant A for some unit time, and is equal to K times A raised to, what power is this A raised to?
1.
Yes, it's raised to the 1. So that tells you this is what type of reaction.
First order.
Yeah, first order. So a lot of times I have the calculus teacher show me how to take integrals of this and derive this thing here. we'll just take his word for it. And it says natural log of the concentration of our reactant at some time t over the concentration of our reactant at time 0 equals negative the rate constant times t. A sub 0 is the initial concentration. A sub t is the concentration at some time during the course of the reaction. Well, we can use our property of logs that says the log of a quotient is equal to what? The log of the difference, really? Right here it is. The log of a quotient is equal to the log of the numerator minus the log of the denominator. That's a property of logs. Then we get this thing here. And then if we add log of a at time 0 to both sides, I get something that looks like this. And once we get to something like this, math teachers feel joy in their heart. So do scientists, because they recognize something. What do you think they recognize?
It's a line.
Yeah, that's the equation of a line. So here's our y equals m, t is our x, and the log of our initial concentration should be some constant. So if a reaction is first order, if we plot natural log of concentration as a function of time, we should get a straight line, and the slope will be the negative of the rate constant. So here's a gas phase reaction, and here's the partial pressure of our starting material, CH3NC, and it goes to acetyl nitrile. And this looks pretty typical. The concentration is dropping and dropping. That's because we're consuming this. And the slope is getting less and less. Rate is decreasing as time is going along. So now if we logify our y-axis here by taking the natural log of these points, we see a beautiful straight line. When the log of partial pressure is plotted as a function of time, we get a straight line, and that tells us it's a first order process. And it also tells us the rate constant. We get this slope be equal to this thing with a negative sign in front of it. And so we get rid of the negative sign. And of course, I get excited about this negative s. Reciprocal seconds. Here is a first order reaction. And so if we just have, once again, I'm going to say a liter flask, so uppercase M just equals moles. It could be moles. We don't really, it's just got to be an amount over time. So if K has S in the bottom, time in the bottom, when we go amount over time, we get a unit of rate. We'll get molarity over seconds. Just as over here, when we just looked at the second order, we get molarity squared. We're going to want molarity over seconds. There's got to be a molarity in the bottom to cancel that out. So if you see a rate constant and its units are given, you know the reaction order. If you know the reaction order, you're going to know the units of the rate constant. That's why I have that slide with them all listed. These are just all in solution. So we're told first order reaction kinetics, and it's consistent with the units on the rate constant. And so that tells us we get to use our handy equation. Only it doesn't quite look like this. It looks like log of concentration sometime down the road is equal to negative rate constant times time plus natural log. So I didn't go off the screen. I'll get it all fit. So this is kind of nice. Once we know it's first order, we can use this equation to find a lot of things. Maybe initial concentration if we're given the concentration sometime into the reaction. If we know it's first order, we can time how long it takes to reach a concentration and then determine the rate constant. So final concentration, initial concentration, and rate constant or time are all the beautiful things we can use this equation to solve for. So now we want to figure out, after 151 seconds, how much of our N2O5 remains.
So that 151 is going to be at the initial concentration, the time.
Right, so here's how we want to approach this. We're going to pull out this equation. It's usually denoted polarity. Alright, negative the rate constant. It's got seconds in the bottom. Time multiplied by time. So here's our initial concentration. You can go ahead and be consistent here with brackets. So now I get to pull out my calculator. So I'm going to go negative 4.82 times 10 to the negative third multiplied by 151 plus natural log 0.072 in parentheses and hit enter. And I got that in the register of my calculator. So our property of logs say, how do we figure out what's inside here? Finding the log of some number is what you have to raise, in this case, e2, since it's natural log. So I have a little e to the x key here, e to the x, my answer in there. And I'm going to just look at this and make it consistent with the data. Any questions about this?